Please go ahead.
Good morning, good afternoon, and good evening to one and all present here. Today, I welcome you all to the lecture 8 of our pCOE lecture series in molecular materials and functions. Today's lecture is by Professor Shobhana Narasimhan, a renowned scientist in the field of computational nanoscience. Professor Shobhana completed her BSc in 1983 in physics from St. Xavier's College, University of Bombay, India. In 1985, she completed her MSc in physics from IIT Bombay with a Institute Silver Medal. In 1988 and 1991, she completed her PhD and MA and PhD in physics from Harvard University, United States. From 1991 to 1994, she did her postdoctoral studies in Brookhaven National Laboratory, and from 1994 to 1996, she continued her postdoctoral research in Fritz Haber Institute, Germany. From 1996 to 2002, she served as an assistant professor in Theoretical Sciences Unit in JNCASR, Bangalore, India. And in 2002, she was promoted to associate professor, and currently from 2008, she's a professor in Theoretical Sciences Unit, JNCASR, Bangalore, India. From 2008 to 2013, she was the chairperson of the Theoretical Sciences Unit, and from 2013 to 2017, she was the Dean of Academic Affairs in JNCASR, Bangalore. So her research interests include computational nanoscience, density functional theory, and materials design. She has been awarded many awards, which are mentioned, some of which are mentioned here, like Institute Silver Medal from IIT Bombay in 1985, Robert L. Wallace Prize Fellowship, Harvard University, 1990, International Union of Materials Research Societies Young Research Award, 1998, Materials Research Society of India Medal in 2001, Kalpana Chawla Women Scientist Award of the Government of Karnataka in 2010, and Sri Shakti Samman Science Award in 2010, Fellow of National Academy of Sciences of India 2011, Anna Boysen Fellowship, TUM Munich, Germany in 2020, and International Honorary Member of American Academy of Arts and Sciences in 2020. So today's lecture title is Diffusion and Sintering of Ultra Small Supported Cluster. Thank you, and over to you, ma'am.
Yeah, thank you. Thank you for that very kind introduction. One sec. I'm having some trouble with my computer. One sec. Can you see my screen?
Yes, not full screen, however. Yeah, now it is.
Yeah, now? Yeah, so I'll be talking today about the diffusion and sintering of ultra small supported clusters. This is a theoretical talk, and I apologize for the somewhat childish cartoons that are on this cover slide. This is a modified version of a talk that I initially made for a general audience. But is someone saying something?
अच्छा है वो भी स्पोर्ट्स में काफी अच्छा काम कर रहा है स्पोर्ट्स में और डेवलपमेंट में तो काफी अच्छा काम कर रहा है ना माइक भी
I'm getting some other sounds.
Yes, kindly mute your microphone. Yeah.
Okay. All right. So most of the work I will present was done by my student Nisha Maman, whose picture is here on the left. Just one result that I will show was done by Rajdeep Banerjee. And most of the work was in this paper, the first paper, the JNCASR paper. So I have a few slides of introduction, and I think this will all be well known to everybody in this audience, but I'll go through them anyway. So as you all know, many catalysts are precious metals. So for example, catalytic converters and cars contain nanoparticles of palladium, platinum, and rhodium as catalysts. And if you look at these metals, their prices are very, very high. So palladium, platinum, rhodium are very expensive, prices comparable to gold. In fact, in the case of rhodium, it's almost 10 times the cost of gold. And so these are extremely expensive. So we would like to use as little of them as possible. So one reason to use nanoparticles is, of course, so that we use less of them. But the other reason to use nanoparticles is that the catalytic activity generally goes up the smaller the size of the nanoparticle. So this is a graph which shows the CO oxidation activity versus the diameter for gold nanoparticles. On this axis is the diameter of the gold nanoparticle. And you can see that as the diameter of the nanoparticle becomes smaller, the activity goes up sharply. So you would generally like to use very small nanoparticles as your catalyst. Of course, there may be some disadvantages in using small nanoparticles. For example, you may change your product selectivity, etc. And the ultimately smallest catalyst that you can have is a single particle. So you have single atom catalyst. And this is, of course, a very hot and exciting field these days. So I've just taken one example from the literature. So this is if you have single atoms of platinum, these are the blue atoms on a Syria surface, then it is a good catalyst to convert CO2 plus hydrogen, carbon monoxide plus hydrogen to methanol. Okay, and so this is, it's been suggested that this could be a way of, for example, storing fuel in a vehicle. But nanoparticles have a problem, which is they're unstable. So again, a sort of childish cartoon, I apologize for that. But so as you increase the size of the particle, as you bring more and more atoms together, the happiness increases. By happiness, I mean, of course, the total energy. So it's more energetically more and more stable as you increase the size of the nanoparticles. So 2 or more nanoparticles or atoms or whatever can always lower the energy by sintering, which is by coalescing. So here I have taken an example where I have taken platinum atoms in the gas phase. So I've taken the total energy of 100 platinum atoms in the gas phase. And I have seen what happens as you coalesce them one atom at a time. So this is 100 atoms in the gas phase. This is 99 atoms in the gas phase, 98 atoms in the gas phase, and 2 of them joined together. This is 97 atoms in the gas phase, 3 joined together, etc., 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 until you ultimately go to 100 atoms forming a nanoparticle. And you can see that as you bring more and more atoms together into a larger and larger nanoparticle, the total energy of the system keeps decreasing. So you can always lower your energy by coalescence. So this means that nanoparticles are unstable. And this sintering is one of the major causes of nanocatalyst degradation. And so you have to keep renewing your catalyst if you have this process of sintering happening. And this is made worse. This problem is worsened by the fact that most nanocatalysts operate at high temperatures. So for example, the catalytic converters in cars operate at temperatures up to 600 Celsius. It may even go up to 1000 Celsius. And you need these high temperatures to overcome the activation barriers for the chemical reaction to proceed, whatever reaction you're interested in. But these same high temperatures also help the nanoparticles overcome diffusion barriers so that they become mobile and then sinter. So, of course, one of the reasons we place the nanoparticles on an oxide support, there are various reasons we do it, but one of this is it anchors them and prevents sintering, but it doesn't prevent it completely. It just makes it slightly less likely. And you still have this problem of sintering. there's a slightly related concept which I just want to introduce. So there's this empirical thing called the Hüttig temperature, which is the temperature at which atoms at the surface of a macroscopic size metal exhibit mobility. And empirically, it is known that it is 1/3 of the bulk melting temperature. So if the bulk metal melts at 900 Kelvin, then around 300 Kelvin, your atoms on the surface of the metal start moving around. Now, similar processes of diffusion and coalescence occur when nanoparticles are deposited on a substrate, though the diffusion barriers and temperatures at which migration occurs will of course be different because you're not on the same metal substrate, you're generally on an oxide support. And so we will look at this issue of what happens when you have it on a different support. So how does sintering occur? There are various possible mechanisms that can happen. So one is called particle migration and coalescence. So this is a electron microscope image of gold nanoparticles on an oxide support. And I will play this video in a minute, and you will see that first, these two nanoparticles will move and coalesce and form one larger nanoparticle. And then this larger nanoparticle and this nanoparticle will move and coalesce to form a yet larger nanoparticle. So you can see this process of sintering. So you see these two have joined and formed one. And now if we wait a while, these two will move and form a yet larger nanoparticle. So this process where both nanoparticles diffuse on the surface and find each other and coalesce is called particle migration and coalescence. I'll just wait a few seconds more to see if it happens. If it doesn't happen quickly, I'll move to the next slide, but I think we're almost there. So let me just wait a few seconds. Yeah, so you see they've approached each other and now you have coalesced into a larger nanoparticle. So the other possible mechanism is Ostwald ripening. This is again a TM image. The reason I put the question mark is I'm not completely convinced that this video shows Ostwald ripening, though that's what it said with the video, that it's showing Ostwald ripening. So in the Ostwald ripening process, larger nanoparticles grow at the expense of smaller nanoparticles. But the way this video looks, I'm not really able to tell the difference here between particle migration and coalescence and Ostwald ripening, because if it was Ostwald ripening, I would expect this one to start looking smaller and this one to start looking bigger instead of this one to just disappear. And another process is what's called monomer addition. So that one, I have a result from a simulation. So let me see. I think I have to change my pointer to make the video play. Yes. So now you see these atoms on the surface are monomers and they will join together. So by the addition of one atom at a time, a cluster grows, so that it's starting to grow in this area. You see that one at a time joins. So right now you have a 4-atom cluster, and as you wait, eventually it'll become a 5-atom cluster, then a 6-atom cluster, etc. And this process is known as monomer addition as opposed to particle migration and coalescence. So the systems that I have studied, I meaning Nisha and I, are ultra small clusters of some metal on a magnesium oxide support. We've looked at the 001 surface. I won't keep saying 001 each time, but it's always 001 we look at. And the metals we've looked at are platinum, palladium, gold, and silver. And the sizes we've looked at are really small: 1 atom, 2 atoms, 3 atoms, and 4 atoms in the cluster. The reason we restricted ourselves to such small sizes was primarily because that was all we could computationally afford, but also because these are the sizes which are of interest if you're looking at things like single atom catalysts. And the surface is either defect-free or it has F centers on it. F centers are oxygen vacancies. So these are the ground state geometries. For example, if you have platinum, so this is a monomer on MgO, this is the dimer on MgO, this is the trimer on MgO, and this is the tetramer on MgO. These are the ground state geometries that we have obtained from our DFT calculations. And we have also taken most of the results have been obtained from our own DFT calculations, but some results we have also taken from the literature. So the computational details, we have performed spin polarized density functional theory. Spin polarized means we can also account for the magnetism of the clusters. Many of these clusters are magnetic. We've used the quantum espresso package. I think there's not much point in my going through all these other details, except to perhaps tell you that the diffusion barriers are obtained by what's called the nudged elastic band method. And some results are taken from these 3 papers. So again, a couple of rather explanatory, simple slides. So apologies if it seems too elementary. So we want to study the thermodynamics and kinetics. So for example, if we have 4 atoms sintering by a process of monomer addition. So these are my 4 atoms. And one of them, say this one moves to join with this atom to coalesce with it. So then I have now a dimer and 2 monomers. And in this process, the energy is lowered from here to here. And then again, I have monomer addition. So this monomer will move and coalesce with this dimer. And again, by forming the trimer, the energy is lowered. And similarly, again, a similar monomer addition occurs to go from the trimer to the tetramer, and the energy is lowered again. And by thermodynamics, of course, what we mean is we are calculating the differences in energy between these various steps. So this energy difference, this energy difference, this energy difference. These are all things we can, of course, compute using density functional theory. But we're also computing the kinetics. So the kinetics are the heights of the energy barriers that have to be overcome to go between each of these steps. And that is, of course, the diffusion barriers. In this particular case, because it's the monomers that diffuse, it's the diffusion barriers for the monomers, the barriers that they have to climb to go from one state to another. And we compute these using density functional theory interfaced with the nudged elastic band method. So let me first show you some simple results for the cluster binding energies. So the cluster binding energies are obtained using this formula. This is, I've shown examples of platinum clusters adsorbed on defect-free MgO. I'll mostly show you results for platinum, but at various points I will stop and compare with results for other elements. So this is the platinum N-atom platinum cluster on MgO minus the bare MgO substrate support minus those many atoms of platinum in the gas phase. So this binding energy has 2 things in it. It tells you how strongly the cluster binds to the MgO support, and it also includes the binding between the atoms in the cluster. So these are the values per atom. So you see that it is obviously dependent on the number of atoms in the cluster. And if we plot these results of the binding energy per atom, Platinum is these pink dots, and then you get lower numbers for palladium, gold, and silver. It's generally monotonic, but not completely so. And if we compute these results, similar results for platinum on MgO, but with the cluster now bound at a site with an F center. So there's a missing oxygen atom. The site of this missing oxygen atom is indicated by this yellow sphere. So when you bind it at these sites, you see the binding energy goes up significantly. So if you compare these four numbers to these four numbers, you see in every case the number is much larger. So the F center results in the cluster being bound much more strongly. And this already suggests that sintering might be more difficult in the presence of F centers. You also will notice certain changes in geometry, most notably, for example, for the dimer. On the pristine, defect-free surface, the dimer absorbs in a vertical position, whereas on the F center, it absorbs in a horizontal position. So we have calculated the diffusion barriers, and I will show them to you in detail, but there are two messages about the diffusion barriers. One is that they are quite complicated. The mechanisms that they diffuse by, they're not simple translational motions at all. And the diffusion barriers are element dependent, and they're quite size dependent. So it's quite a messy scenario. So for example, here I've just put the results for platinum, and I've said the mechanism by which it will move. So this is a hopping mechanism, a cartwheel mechanism, what I call AT-AT walking, and what I call rolling. I'll show you pictures, I'll show you videos of what all these mechanisms are in just a minute. So this is for diffusion of the monomer, the dimer, the trimer, and the tetramer. So you see that every time you're adding an extra atom, the mechanism of diffusion is changing. And also, of course, the diffusion barrier itself in some rather complicated way. And if I take just the monomer and look at different metals, so the diffusing monomer is platinum, palladium, gold, or silver, then for the particular case of the monomer, there's only a single mechanism possible, which is hopping, but that's not true for the larger clusters. And you see the diffusion barriers are quite different for the four metals. And now I add the dimer, and now again, I start seeing different mechanisms. And so this is my full table of mechanisms and diffusion barriers. And it looks very complicated, but the surprising thing is there are, there are certain patterns in here, and we will extract them and discuss them with you. So monomer diffusion on platinum. The monomer, the only way the monomer can move is by a simple translation motion, which is called hopping. And if we calculate the barrier, it is like this. So the minimum, the global minimum is when the platinum atom is sitting over an oxygen atom on the surface. And the transition state is when it is at a bridge site, okay? And we can calculate this energy landscape. And the barrier for this diffusion is 0.88 eV, which is reasonably high. Now we go to the dimer diffusion, the diffusion of a platinum dimer on MgO. And we see that it is a much more complex mechanism. You alternate between having the dimer vertical and horizontal on the surface. So this is like this cartwheeling mechanism. Incidentally, in this process, it also switches between being magnetic and non-magnetic. If you look at the global energy minima, but during the diffusion process, it's not clear that the spin can change. And the energy landscape looks much more complicated. And if you look at the barrier from here to here, it is 0.42 electron volts. And if you look at the trimer, there's yet a third mechanism. Initially, we were calling it skating or walking, but then I kept thinking this reminds me of something. And finally, I decided what it reminds me of is, I don't know how many of you have seen the early Star Wars movies. In them, they have these transport vehicles called AT-AT walkers. And the way this cluster was moving on the surface, it reminded me most of an AT-AT walker. So I decided to call this AT-AT walking. And once again, we can calculate the barrier for this diffusion, and it comes out to be 0.60 electron volts. And if you look at the platinum tetramer, then you have yet another mechanism, which is rolling, which is, it has yet another, it's completely different from the three previous mechanisms. And you now have a barrier of 0.8 electron volts. So what do you do with all this? Are there any trends in the diffusion barriers? So if I look at just platinum, it's not clear that there's any trend. Unlike the binding energies, which had, it seemed at first that they had a simple trend, but the diffusion barrier looks much more complicated. And then if I put all my results for diffusion barriers together, it looks like a huge mess. Okay, but the somewhat surprising thing is that there is actually some trends hidden within this, which I will now show you. So we want to look for scaling relations. So now I will remind you of this thing I told you about at the beginning of the talk called the Hüttig temperature, which is the temperature at which atoms on the surface of the metal start becoming mobile. And I told you that empirically, it's said to be 1/3 of the bulk melting temperature. So we want to know whether we can make any similar statements for sintering temperatures for these ultra small metal nanoclusters on MgO. And motivated by this, what we plotted was the diffusion barrier versus the bulk melting temperature of the metal. And I mean, it's not a perfect relation except for the trimers, but it's pretty good, okay? I mean, you do at least always get them in the order silver, gold, palladium, platinum, silver, gold, palladium, platinum, silver, gold, palladium, platinum, except for the dimers. Okay, so let's remember that it didn't work for the dimers, but it worked for the others. And so the diffusion barrier seems to scale with the bulk melting temperature. And this is pretty surprising. I mean, it's kind of non-intuitive, at least initially. So when we got this result, it wasn't clear to us whether this was just some sort of weird coincidence, or can we understand anything more about it? So we showed these results to various people who work in the field, and most of them said, I don't understand this. This has to be a coincidence. This can't be right. Why should the diffusion barrier of, say, 3 atoms of the metal on MgO have anything to do with the bulk melting temperature of that metal? And I have to say the referees also initially howled with outrage. But we think we can explain the scaling relations, and I'll do that now. So it's a 3-step argument we have. So the diffusion barriers, we first correlate with the binding energy of the cluster to the support. Then we then correlate with the cohesive energy of the bulk metal. That's the second step. And that in the third step is correlated to the melting temperature of the bulk metal. And so if you can prove this, then you finally prove that this diffusion barrier is correlated to the bulk melting temperature. So let's check the first step. So on this axis, there's the diffusion barrier, and on this axis is the binding energy of the cluster to the support. And you see that you get, well, palladium falls off a bit here, but in general, you get a pretty good correlation, except for the dimers where it totally fails. Okay. And as I said before, again, EB and ED both follow the order AG less than AU less than PD less than platinum. Okay. And palladium does fall off on this graph, but we sort of understand why. Okay. And notice this almost perfect correlation that you get for the tetramers, which is kind of surprising because there are 3 different mechanisms here. The AG tetramer moves by what's called a rocking mechanism. This moves by what's called a shuffling mechanism. And these 2 move by this rolling mechanism. So it's quite surprising to find these kinds of correlations. But these kinds of correlations have been noted in the literature before, though not for metal clusters on oxide supports. Instead, they have been for adsorbates, small atoms or molecules on metal supports. So this is by this group of Mavrikakis, who showed that if you plot, this is the diffusion barrier, that is the height of the transition state, versus the binding energy of the initial state, then you get a pretty good linear correlation. The reason the slope looks the opposite way from my graphs is because I define the binding energy with an additional minus sign, which they haven't done. So their binding energies are negative. And so they have the slope this way instead of this way as I do. So why does this happen? Why does the diffusion barrier correlate with the binding energy? So supposing we can think of the energy landscape of diffusion as a superposition of parabolas. Okay, so here I have drawn these parabolas, and this green thing is my energy landscape on which I'm diffusing. Then the depth of this parabola, the depth of this minimum, gives me the binding energy. And this height here, where the 2 parabolas cross, is the diffusion barrier. So if I draw 2 different energy landscapes for the case of metal 1 on MgO and metal 2 on MgO, you can see that if I make the binding energy stronger by making this wells more deep, then automatically the diffusion barrier also increases. So if I have that for metal 1, the binding energy is more than for metal 2, then it means also the diffusion barrier is more for metal 1 than for metal 2. This is sort of similar to the argument that people use to justify the BEP relation in catalysis, though it has some important differences, which I can discuss if people want. So, but for this argument to work, the energy surface between the global minimum and the transition state has to be roughly parabolic. So let us look at what we have. This is the monomer, the dimer, the trimer, the tetramer for platinum. And if you look at them, you see that for the monomer, This is the minimum, this is the transition state, looks roughly parabolic. For the dimer, it is not parabolic because you have this additional minimum in between. For the trimer, it's parabolic. For the tetramer, it's parabolic. And so now we understand why this argument failed for the dimer. Okay, so for some of the cases in the dimer, you have this additionally more complex energy landscape for the along the diffusion path. And so this simple argument fails, and that's why you don't have this correlation. Now let's go to the second step. The cluster binding energies correlate with the cohesive energies of the bulk metals. This seems quite reasonable. You break some bonds in going from the bulk to the cluster, and then it wants to compensate for those missing bonds by making bonds within the cluster and from the cluster to the surface, and it will make them stronger depending on how strong the initial bonds were. And again, you find a pretty good correlation in this case, in all 4 cases, because you are not depending on the energy landscapes topography over here. So now you put these together and you plot the diffusion barrier versus the cohesive energy. And again, you get a pretty good correlation for the monomer, for the trimer and the tetramer, but not for the dimer for the reasons I've already discussed. Now we want the third step for the cohesive energies to correlate with the melting temperature. This is actually well known in the literature. It follows from something called the universal bulk binding curve. So this is not our result. This is known in the literature from quite a long time ago, from 1984, that if you plot the cohesive energy versus the bulk melting temperature, you get roughly a straight line, and it's given by this equation. And for our particular cases, we plot the results and we see, notice that palladium falls slightly off the line, which is well known for palladium that it falls slightly off the line. And this is the reason why the plot points for palladium fall off some of our correlation lines. So we have shown that diffusion barrier correlates with binding energy correlates with cohesive energy correlates with melting temperature, and therefore the diffusion barrier correlates with the melting temperature. But for this to hold, the topography of the energy landscape between the global minimum and the transition state has to be roughly parabolic. This is not true for dimers, which is why the scaling relation doesn't hold for the dimers. And we can find similar correlations for self-diffusion. I mean, this is not what we were initially interested in, but then we wanted to know, can we somehow try to derive this Huttig scaling relation for self-diffusion, that is, metal atoms on the metal substrate. So we looked at the metals on the 111 surface. So this is just monomer diffusion. So you find the diffusion barrier correlates with the binding energy correlates with the cohesive energy. So the diffusion barrier correlates with the cohesive energy. And then you have more or less the scaling relation that the diffusion barrier correlates with the melting temperature, though palladium falls off. Now, I mean, this is actually really unlikely, you know. I mean, you just have one metal atom on MgO. So it seems really unlikely that it should have anything to do with the bulk melting temperature, but it seems to follow at least roughly. So this is a rule of thumb. And if you assume that the metal atoms become mobile at some temperature, such that the diffusion barrier versus KBT is some fraction, then you get the temperature at which the metal atoms become mobile. You get an equation like this. So this, some fraction of the melting temperature is the Huttig term, and we get this extra term. So basically what we've done with all this is said that we, if you want to prevent sintering, you have to have a metal with a high melting temperature, and that this will hold even for very ultra small clusters. And this may seem intuitive, or it may seem counterintuitive. I don't know how you feel about it, but we have justified this argument. So let me, I think I'm almost out of time. So let me talk a little bit more about sintering now. So the energy gained by sintering. So if you take a cluster with n minus x atoms and a cluster with x atoms and put them together to make a cluster with n atoms, you gain energy. So that is the sintering energy. And we can plot the sintering energy versus the size of the cluster for platinum, palladium, gold, and silver. So let me talk about this. So we can also study the process by which the sintering occurs. So for example, say I want to see how a platinum dimer on MgO is formed, trimer on MgO is formed. So I start with 3 platinum atoms. First, 2 of them come together to form a dimer. Now, when I want to bring them together to form the trimer, 2 things could happen. The platinum 2 could diffuse, or the platinum 1 could diffuse. And in the particular case of platinum, the barrier is lower for the dimer to diffuse than for the monomer to diffuse. So this is more likely to happen than for this to happen. But this is metal dependent because, for example, if you look at gold, it's the other way around. It is much more easy for the monomer to diffuse than for the dimer to diffuse. And we can do this kind of diagram for all the metals we have studied. Let me show you the consequences, okay? So let's see how a platinum tetramer forms. So if I look at every step, so first step, 1 atom diffuses and it forms a dimer. Then the most favorable thing is for the dimer to diffuse and form the trimer. Then it is most favorable for the trimer to diffuse and form the tetramer. So if I look at this, I have growth by monomer addition. That is, I have added 1 atom at a time, but it's in a very unexpected way because people till now always thought monomer addition means that a single atom, the monomer, diffuses and joins the larger cluster. But in the case of platinum, at least at these small sizes, we find that the opposite is true. It is more favorable for the larger cluster to diffuse and join the monomer. Whereas if you look at gold, okay, so the first step is the same. In the second step, it is more favorable for another monomer to join with another atom to form yet another dimer. Then in these 2 dimers, the dimers diffuse and form a tetramer. So for gold, it's a different mechanism. It's growth by particle migration and coalescence. So if I look at the effect of F centers, for the effect of F centers, we've made this assumption, which probably isn't completely valid, which is we've assumed that the diffusion barriers don't change because of the F centers. We've assumed that only the initial and final states change. And if we look at that, if we look at the change in free energy that occurs due to sintering, you see that the change in free energy is much less when you have F centers. And so here, an atom with a white circle indicates that it is sitting on an F center. And so the sintering becomes less favorable in the presence of F centers. Similarly, now for a larger cluster size. So I'm done. What I wanted to just remind you, I've studied ultra small clusters of precious metals on MgO. So I've My talk's been a bit different from the earlier ones in the series where people gave you maybe an overview of a field. I've chosen instead to take one specific problem and tell you in detail what we've done by it and what we can extract from it. We find that the cluster is diffused by non-trivial mechanisms, not just simple translations. And the diffusion barriers scale with bulk melting temperature if the energy profile is roughly parabolic. And the clusters become mobile at some temperature, which is some constant plus a fraction of the bulk melting temperatures. The sintering mechanisms are metal dependent and can be monomer addition or particle migration and coalescence. Having F centers hinders sintering. And okay, one thing I forgot to discuss, but you can see is that you get opposing trends from thermodynamics and kinetics. So if you look at this picture, for example, in the case of platinum, if you look at the energy you gain by sintering, it is huge. It is much bigger than for the other elements. On the other hand, the barriers you have to climb are higher for platinum than they are for the other element. So in the short time scale, when you're looking at diffusion barriers, you would say that it is least likely for sintering to occur on platinum. But on the other hand, if you wait for long time scales with thermodynamics wins out, you would say platinum is most likely to sinter. So you have opposite trends from thermodynamics and kinetics. So that's all I wanted to say. Thank you.
Very nice, Shobhana. Let me begin by asking one question and then probably ask others to, in case they have questions. In general, catalytic supports would play a very big role here, and good supports or huge supports are silica or zeolites or something. One question is that the lessons that you learned about how particles move and a series of metals, how you correlate their behavior with their bulk melting point and parameters of this kind, are they valid for a range of substrates?
I would think so, because the arguments are quite general. So I would think that, for example, I mean, they're very general. I mean, they're sort of commonsensical things. It says that if you bind strongly to the support, then your diffusion barrier is also going to be high, which is sort of intuitive. If you bind strongly, you're not going to diffuse. So, but of course, but this doesn't say anything about the catalytic activity. So so you have to simultaneously optimize. I mean, the support affects the catalytic activity, which is something I haven't looked at. I've only looked at the sintering in this problem. But
the second thing is that when you start looking at a metal like silver, gold, palladium, and platinum,
yeah,
you see the chemical reactivity of these systems to oxygen. That's significantly different. I would expect palladium to form an oxide.
Yeah.
Now, why this is not really possible, and that would probably change the palladium's behavior quite significantly.
Yeah, that's true. I have just looked at their behavior in vacuum, and I have not taken into account whether they oxidize and then how the barrier would change if it oxidized, etc.
So the last thing that I wanted to know was that the dimer, why can't it roll on the surface?
I don't understand why it doesn't, but we have tried it, and it is just energetically unfavorable. And that seems to also be, and the mechanism is also metal dependent. And I don't understand completely why, because you would expect the nature of the bonding to be roughly similar in these atoms. So maybe if we look at the electronic charge densities and look at the directionality and stuff like that, maybe we will get something. But the mechanism for the dimer, it doesn't want to roll. And it is also different. I mean, it is not the same cartwheel on all the surfaces. It's on 2 of the surfaces, it's cartwheel. On one, it is hopping. On one, it is something called partial dissociation. So it is metal dependent.
All right, I'm done with my questions. Colleagues, if you have questions, please unmute yourself and ask your questions.
Can I have a question?
Yes, Thomas, yeah, please.
Thank you. I'm sorry for joining later because of some other things, but I've always been wondering whether molecules move over the surface in a slippery. I'm not an expert. I'm not a computational scientist, but I've always been wondering whether molecules move in a slippery way, or whether they kind of roll. And I liked the part of your presentation in which you showed how the molecules can roll over the surface. And what always comes up in my mind is, can you see such a movement of such a small cluster experimentally in high vacuum using STM? Is it even possible to distinguish by, for example, lowering the temperature at which you still can see some movement of these molecules, and it might be a kind of a directional movement depending on the orientation of the substrate surface? So can you make a correlation between experimental results and computational results, and how difficult it is? Because I can imagine, for example, with gold, where there is this herringbone reconstruction of the surface, which is rather, I would say, from my perspective, as I've always looked at it, rather difficult to somehow make a model of because of its long-reaching distance.
Yeah, so but here the substrate isn't gold. It is.
Yeah, I know. But can you make the correlation between experimental STM and these little clusters and so how they move?
So I've been talking to someone, Friedrich Esch at TUM in Munich. I don't know if you know him, but he is exactly seeing this. He thinks he does STM, low temperature STM, and he thinks he can see that the clusters roll, but he has done it for other systems and other supports. So he hasn't done it for the same systems as me, but he certainly thinks he sees that these non-trivial systems of diffusion, mechanisms of diffusion.
That's exciting. So during these steps, when the little clusters, when they move over the surface, can you like identify, for example, changes in the frontier orbitals when you look at it using scanning tunneling microscope? Can you see changes in the appearance of the molecule of the cluster on the surface, and do a correlation between the frontier orbitals as calculated and as you can visualize them using STM?
I don't think anyone has done it, but it's certainly possible to do it, because we have done it. For example, we have done it for larger systems, like we have a molecular rotor on a surface which is rotating, and we have done simulated STMs and experimental STMs in another project, and we can see them matching. And then if we look at the charge densities, we can actually see the hydrogen bonds being broken and formed as the molecule rotates, and correlate it with the energy landscape, etc. So I think this is something that can definitely be done.
That's fantastic research. Thank you very much.
Thank you.
I enjoyed it. Thank you.
Very nice. Colleagues, are there other questions?
Can I go for a question?
Go ahead, Suraj.
Ma'am, I have one question related to this, the mechanism. So is it possible that the way you are showing, it was like once a dimer is formed, then a trimer formed and it rolled to the fourth one. So is it possible that two this metal cluster with a dimer, two dimers are formed, then these dimers are going to combine?
Yeah, so that's what I actually showed, that, I mean, we looked at which is more energetically favorable. So for gold, I found that it's more energetically favorable for two dimers to form and then form the tetramer, whereas for platinum, it was more favorable for a dimer, then a trimer, and then a tetramer to form.
Okay. One more question I have, that how the oxidation state of the metal adsorb is going to affect this mechanism. For example, the palladium, it could be in the PDO state, like palladium oxide kind of form may be preferred. So it might be binding to only one oxygen. And
Yeah,
in gold,
so that's what I've said. I haven't looked at oxygen at all. I've just assumed that it's in, ultra high vacuum or whatever, and there's no other species.
Yeah, even after adsorbing onto the surface, it could be in the connected to that oxygens, right? And depending on the nature of the metal, the kind of binding would be, kind of binding would be different.
Yes, so all that we of course account for automatically. We haven't actually analyzed what the oxidation state is, but that is something we can easily do as post-processing from our data.
Yes.
The other thing that maybe somebody has some ideas for me, but I mean, I don't think it changes the diffusion barrier significantly, is my feeling, but if you actually do a global minimum or a minimum search, sometimes the global minimum is non-magnetic, but the transition state is magnetic. And I don't know if the spin configuration can actually change along the diffusion path, or whether you have to constrain the spin to be constant. I mean, we didn't worry too much about it because it didn't make a big difference along in the results we finally got. But I would like to understand what is physically more meaningful. Can the spin state change, or should the spin be constrained as you move along the diffusion path?
So that connects me to what question I wanted to ask is, Suraj, let me just jump in and ask this question. That was, you said in the course of that diffusion, the spin state changes. So can one do a measurement of magnetism to understand diffusion?
Yeah, so I honestly don't know this. That's what I'm saying. I don't know if it is physically meaningful to say. I mean, I can say the spin state changes if I allow the spin degree of freedom to be optimized along with the geometry. Then I can say that in this configuration, it would prefer to have this spin than this spin. But I don't know if that is physically meaningful, if it actually happens or not. I don't know.
Okay, Suraj, you continue.
Yes, madam. I also felt that whatever your diffusion barrier, it may not be affecting unless you are considering that spin state into consideration. Otherwise,
no, the diffusion barriers don't change much because the energies between different spin states is small.
Okay.
And therefore the diffusion barriers don't change much. So the conclusions of this project didn't change much. But it wasn't clear to us whether we should constrain the spin or not.
Okay. So I believe that trend can be explained if we analyze the nature of the oxidation state or the kind of bonding that is the metal cluster have with the support.
Yeah, obviously, if you want to understand why the mechanism is different for different metals, then it has to have something to do with the different bonding, right?
Yes.
Okay. Any other question?
Sir, may I have some questions?
Sure.
I have some questions. So first of all, thank you, madam, for this nice presentation. And I have like query regarding this when you say or this when you observe the mechanism of absorption of this monomer to tetramer on MgO, then how do you theoretically means observe this mechanism, like you are saying, like this is rolling or something at working, means how do you theoretically observe this one?
So it actually comes out of the calculation. So in the nudged elastic band, you give an initial state and a final state, and it finds the minimum energy path between the initial state and the final state. So for example, if the initial state, so if you find your global minimum state is, say, adsorbed atop an oxygen, that's your initial state. Your final state is adsorbed over the oxygen in the next unit cell.
Okay.
And you say, find me the path to go from here to here.
Okay.
Now, of course, it's not always that straightforward. Like sometimes you have to give some intermediate images. You might have to do some guesswork. You might have to say, try this, try that, try that. But in principle, if you just do it, the algorithm will find for you. It will take the system along the minimum energy path, and this will come out of it automatically.
Okay. Okay, madam. Thank you.
Okay, then I suppose we should close this. We are at 7:34. Thank you, Shobhana, for that wonderful talk. And then it has, of course, stimulated a number of questions. And especially Thomas would like to, because he studies small, well, boranes, carboranes, and all that on surfaces, their movement and STM and things like that. And there are a lot of possibilities with these. And I was curious to know how clusters really, the kind of clusters that we work with, which are protected and are with a few ligands, and how they move around. And then that leads to crystallization of these clusters, thin films of.
I think those are things we can look at also if it's not too big, you know. Because as I said, we've been looking at these organic molecules and their diffusion. In other projects, we've been looking at organic molecules on surfaces and their diffusion and things like that. So,
yeah, you know, this one can simulate also images, STM images, and this is something that Thomas would be, you know, very interested in exploring. Yeah.
Yes, because we do indeed see that when we have a flat surface, and there is a nice link to what we are developing with Pradeep, with the small clusters, but on a flat surface at very sparse coverage of that surface, we do see some of the carborane thiol molecules moving over the surface. So, and it's kind of directional. Of course, it's linked because we do most of our experiments on flat gold surfaces. Then we see the herringbone reconstruction under ultra high vacuum, and we do see the molecules to move over the surface. And there is this link to this joint work with Pradeep, that if we have very small clusters and how mobile these carborane thiolated molecules are on the surface of the metal clusters. So it's kind of interlinked, and I'm sure that we could come up with a reasonable model for simulations using these smaller clusters, which could be computationally somehow easier approachable than, for example, those bulk surfaces with herringbone reconstruction that seem to me, at least, to
the
be
herringbone
rather
reconstruction
very,
would be impossible. Yeah,
very difficult then.
Yeah, but I'd be very happy to discuss more if you want to sometime.
Yes, that would be nice. Well, we can perhaps maybe organize with Pradeep some session and to discuss some of the systems that we have, and I might show you the mobility that we observe on the flat surface, and yeah, to maybe tackle some of those small metal clusters with carborane thiolate ligands on them, and to explain the stability and the mobility of the clusters on the metal clusters, because I'm talking about clusters, but these are like carborane clusters on the surface of metal clusters.
Yeah, I understand.
Yeah.
Okay, there are many related things. For want of time, I'm not going to get into those. So just to give you a teaser, on a cluster surface, two ligands sitting there, we study one ligand here, another ligand here. After some time, we look at it, one ligand here, another ligand there. So this fellow is moving around on a three-dimensional surface. That's something we still, nobody knows how this motion is. But with NMR, one can study these.
It might be more interesting to do it with a force field or something. I'm not sure. I mean, if the force field is good enough, you should be able to look at it directly.
Sure. I think, Thomas, if there is a time available, Shobhana is in that email group, see whether some common time can be found for a discussion someday.
Yes, I agree. So shall we stay in contact over email and discuss some reasonable time?
That would be great.
Okay, I'll be happy to as well. Thank you very much.
Okay. All right. Bye.
Yeah. Thank you, Shobhana.
Bye.
Thank you.
Okay.
Thank you.
Thank you, Pradeep. Thank
Right.
you, Pradeep. Bye.
Thank you. Bye-bye.